Someone's logged in. Let's just wait for the others to join in. It's still early. Just made sure that the streaming is working because sometimes the Wi-Fi here is a little wonky, building D, so we just have to. Oh, Nawaf is still there. Hello, Nawaf. While waiting for the others, if you can grasp your notes, especially the reduction potential table, if you can flip to page 6, just getting ready. We might need this page here when we do our discussion. Okay, I hope you're also logged on to Schoology. So we will discuss something first, then I will guide you through an activity. Morning, Abdallah. Maybe I should. The other one here. So I have Yasid, Nawaf, Abdallah, Fawaz, Badr. Hello, Abdul Malik. Oh, it's Amar. Okay. Quite a handle. 3 minutes more. Rakan, hello. So how many are we now? I have 8 people here. Muhammad. Which Muhammad is this? Ah, Shamari, hello. I can imagine you seated here. I can imagine your faces here. Again, if you can grab your notes, if you have them with you, or yeah, we are staying in our classrooms because the administrators might be, going by and see, they want to see. Someone might pop up here and look at what we're doing so they can see what we're doing in class. Again, if you can have access to the reduction potential table, be it from our notes or you have a book, or you can just search online so that we can have a reference. bother not doing his work? I don't think so. He always does his work. Well, you'll know it when you're already working. Even if probably it's flooding, we're still here. Because for us asking why don't they send us home? Well, that's part of being here. Because the directive among employees is not to we're not on house arrest yet. Everybody has to go to the office. Only 9 people so far. We haven't heard anything about the extension, but at the rate that the virus is spreading, it's really bad. So we will just have to wait. That's why if this works, we can have this. This is a better communication way because we can discuss. You can see what we're doing here, and then you can comment, and I can address your questions. And we can save this actually, so we can go back to the video and see if we have missed something about the questions. Yeah, right. So to answer that question, Muhammad, we don't know yet. Of course, I will be updating you, or the administration will be updating you if we're going to extend soon. Okay, it's officially 10 o'clock, so we'll just wait a few more moments. So Ryan is here. Hello. Hello, Ryan. So Ryan joined in. We have Ryan, Rakan, good morning. And he said, oh, Saeed is on Schoology. I'm not sure if they're live on YouTube. Sorry, that's all caps. Who's Kevin? Weird. Who's Kevin? Good morning to you too. So Saeed is Kevin. Quite an interesting name. Excuse you. Okay, don't start, guys. Let's wait for the others to tune in so that we will not be losing a lot of time. So we will be doing 2 periods today, as you know it. There are already 2 activities waiting for you there, but most likely there are salient points that we need to discuss as we go along. Rayan Salama, yes. And Rayan Algaundi before. Okay, the 2 Rayans are here now. 13. Who else is not here? 13. Where's Muhammad Al Sultan? Where's Sultan Al Gusani? And Suleiman Al Sayari. Suleiman already here. Hello, Suleiman. Who are you, LMCA? That's Muhammad Al Shamri. That's why you need to come up with, so everybody's comment now has a channel. Later on or next week, if we continue, when we do live streaming, it will just be for subscribers. So we cannot just make this public so nobody else can just a great person. So Ryan, who is very much into physics, we will see. I hope the 2 videos that we have watched previously with Tyler DeWitt is good in terms of very basic information. He's very good at it. We have seen how creative he has presented the topics now. We can deal with a little bit more focusing on, getting it on with the items that the AP is practically asking from us. Someone dislike my stream, that's fine. It's not for them if they don't like it. We have to discuss things now. 13. Okay. Okay, guys. So we might as well go on with it, right? Ready? So give me time to discuss things first. Okay. Sultan is right here. Hello, Sultan, finally. And we just have to discuss some of the few things, and then we will be able to look into the salient items. Okay. Now, I hope that you can see what's on the board. I'll try to write larger items. Now, we'll go back to galvanic cells. That will be our discussion for now, and then talking more about the E naught. Remember, E naught is very much under standard conditions. When we say standard conditions, that would be 25 degrees Celsius and 1 bar pressure. That's SATP. But here I've added that since we're dealing with a lot of mixtures now, before when we talked about standard conditions, we just talk about pure substances, solids in their pure state. You have gases. When we say gases in their standard conditions, that would be they are at 1 atmosphere, and we're dealing with aqueous medium, that would be they should be at 1 molar. Okay, so let's say we are asked to construct a galvanic cell. Remember that a galvanic cell is a device that makes use of a spontaneous reaction, which means we can generate electricity from it. Okay? Remember how I told you that every change there is a driving force, right? You can comment on that. Okay? Remember that heat transfer is happening because of a difference in temperature from hot body to cold body. The driving force is practically the difference in temperature. Now here, we have already been introduced. What's the driving force for the electrochemical reaction? It's the electromotive force. That's the cell potential. That's the difference in electric potential between 2 points. And where does that come from? The tendency of chemical species to push or to pull electrons. That's why they came up with a reduction potential table so that we can tell which one has a greater tendency to give up an electron or rather be, receiving them. So let's say we have here, let's take the standard hydrogen electrode. So the reduction potential of the standard hydrogen electrode, you can see here hydrogen gas. This is our reference electrode. Okay? Now, this is called a reference electrode because every other half cell is pitted against this. This is a reference. We put this into 0, so the partner will get its own potential, either an oxidation potential or reduction potential, depending on its reactivity with the H+. Okay, so that's our reference. So let's say we partner that up with a silver electrode. Okay, so here, your silver gets reduced with the standard hydrogen electrode. We see there it's giving up a solid silver with an E naught of positive 0.8 volts. Okay, so if we look into their tendency to push or pull an electron, we see here that the silver ion, okay, has a higher reduction potential than the hydronium ion, or the H+, as you see here. So that means it would rather take the electron than the H+. So if we want to construct a cell, remember we should come up with a positive value, right? So that it can be spontaneous. So our reference is that if the E cell under standard conditions is greater than 0, so this is a depiction, or this signifies a spontaneous reaction. That's our basis. Now, since silver ion has a higher reduction potential than H+, then this is the reduction half that will happen. In other words, this has to flip, meaning it has no choice but to do oxidation instead. Remember, in a redox process, one gets reduced, the other gets oxidized. Okay, so here we say, I will now put this as our, remember this, RHR from trimester 1, reduction half reaction. So that would be our silver ions getting reduced to silver solid. And we will, now I'll put this subscript red here for reduction so that we are referring to the reduction potential. So that's 0.8 volts. Therefore, we have to reverse this reaction so that we can have a full-on transfer of electrons. Because this requires electron, we need something that gives up the electron. In that case, that will be our oxidation half reaction here. So your hydrogen gas, which is in your standard hydrogen electrode, will now be producing more of your hydronium ion, and that will be giving up 2 electrons in the process. And that will be our oxidation potential here. 0 is still 0, right? Now, look at that. Silver would require 1 mole of electron for reduction, while hydrogen gas is giving up 2. So we need to balance the reaction just like what we did in trimester 1. Okay, remember the number of electrons lost is the same as the number of electrons gained. So we need to multiply this by 2. Okay, now remember the reason why we multiply this by 2 is to balance the number of electrons lost and gained, but we are not multiplying this by 2. Remember, the reduction potential is with reference to the standard hydrogen electrode. So that is the same for everything that you see on the table, okay, the reduction potential table. So the only, the same thing that we did here in terms of what we know about like Hess's law when adding up reaction is when we reverse the reaction, we reverse the sign. But for the E naught value, we don't multiply it by a particular factor. I hope that's clear. So when we add these 2 reactions, we add the reduction in oxidation potentials, okay? So that will be your E cell. That will be the potential of what is happening in the oxidation part and what is happening on the reduction part. So this gives us, obviously, a positive value. So what we can get from here, yes, we can construct a galvanic cell here that can generate 0.8 volts under standard conditions. So what's the overall reaction? So the cell reaction can be written, you just have to copy this, 2 silver ions, okay, plus the hydrogen gas, giving up, say, 2 silver solid, 2 hydronium ion, okay? So that's 2 silver, 2 hydrogen. So this is our overall cell reaction, okay? Right in the room, hello. Identify the overall reaction. Now, the next thing is we need to construct the cell, okay? Remember, when we construct the galvanic cell, it's like reading from left to right. Normally, what happens in the oxidation is put to the left, and then we put the other one on the right, which is our reduction. So our oxidation here is our hydrogen gas converted to hydronium. So we will put that in our anode half cell, okay? So that means we have to have a way of bubbling our hydrogen gas here, which is practically a contraption in your hydrogen electrode, okay? And then, of course, it's immersed in a acidic solution, right? In the other compartment, that is where we have our silver ions, and then you have your silver metal. See, this is reduction, so silver metal is our cathode. Okay, I hope you're catching this. Now, an electrode should be a solid. Okay, we cannot use a liquid for an electrode. Since it's the hydrogen and the H plus that is doing the reaction, we need an electron sink that will connect the 2 electrodes. So in this case, we need an inert metal, okay? And that is practically your platinum. So your platinum here, okay, working, and then connect that into your cathode here. So your platinum is our anode, right? And then don't forget that we need a salt bridge to complete the circuit. Remember, just like in any electrical circuit, a physical one, completely conductive, electrical, not electrolytic, we have to have a continuous movement of charges. And that is the role of the salt bridge. Okay, so let's say we have a saturated sodium chloride solution here. Okay, so here what happens is that the oxidation happens here. The oxidation is where, or rather, the anode half cell is where oxidation happens. This is where the reduction happens. Okay, which one is the anolyte? The specific electrolyte. Okay, what's there? Does E not reverse signs when you flip the reaction? Yes, Said. If we do it here, what we did here was we flipped this equation here. But 0 is still a 0, right? So that's why you don't have to flip the sign because 0 is a 0. If it's like positive 0.3 here, it becomes negative 0.3 there. Okay? So your activity, practically, will be doing that. Okay? I think questions are after the lecture, which will take 25 minutes. Is the stream lagging for you guys? Okay, there will always be issues about connections, so but this will be, saved a little bit later. Now, look at that. If you have questions about the setup, if there's something unclear, just put it in the comments. We can discuss that later. Now, the next thing that we can do is to write the cell notation. Okay, remember the cell notation, it's like a shortcut. We call that a shortcut so that we can visualize this diagram that we have done. It's like anode half reaction separated from the cathode half reaction. Okay, so this is where the anode is reacting. We start from the electrode. So we need to put platinum in there. This is our anode. Repeating that. Platinum is our anode. So it's physically separated from our anode half cell. The anode half cell is between what? The hydrogen gas. Okay. And then physically separated also from the hydronium ions. And then you have your salt bridge here. So this is aqueous. What's happening in the reduction part? It's the silver ions. And then that's your silver solid. So this is our cell notation here. So what this cell notation is practically telling us is that, look at this one here. This is our anode. This is the source of the electron. Remember, this is the oxidation part. It gives off the electrons. So it's not the platinum that gives off the electron. It's just there as a conduit. Remember, we need an electron. Either they are reacting or not. It has to transmit the electrons through the external circuit. Okay, so your platinum will be connecting that to the silver. Okay, let's make this a little shorter. So we can put a voltmeter here. So the electron will be traveling from your anode, going down here, and then it will be captured by your cathode. Your cathode here is the silver solid. Your anode here is the platinum. Okay, this is your oxidation half reaction, right? And this is your reduction half. Okay, notice that I made bars here because these are all different physical boundaries. Okay, a solid different from a gas, and a gas different from the one dissolved in solution. In as much as silver ions here are dissolved in water, and then you have your silver solid here. So here, the potential difference, you can see from the tendency of these reactions to occur, is based on the reduction potential. What we're trying to say here is this. If you are asked the same way, if you're given a set of reduction potentials, you are asked to construct a cell, of course, you have to determine which is the oxidation half and which is the reduction half based on their reduction potentials, because you will have access to those values anyways. Then come up with an overall cell reaction. Determine the E naught of the cell. Okay, the E naught of the cell should be positive for it to be tagged as a galvanic or voltaic cell. There is another type of cell which occurs in reverse. We are pushing for the electrons. We are paying for the electrons. That's an electrolytic setup, so that's different. A galvanic cell or a voltaic cell is one that can generate its own electricity. Okay, then you should be able to draw basically your galvanic cell like this one here with a salt bridge, and then you should be able to arrive also at the cell notation. Okay? Or we can totally reverse the process, meaning I can give you the cell notation. You should be able to deduce the reaction from the reduction potential table. Okay? So for now, let's see. Let's consider some questions here before about the salt bridge. So the platinum electrode is not involved in the reaction, right? Yes. And its physical shape doesn't change like copper and zinc reaction. Well, if platinum, to answer that question first, we'll go to the salt bridge, okay? If platinum is not part of the electron transfer, it's just a what? A channel by which the electron is traveling. Its mass should not be changing, right? Because nothing gets deposited in it and nothing is removed from it. Why? Because the species reacting in this case are hydrogen gas being converted to H+. We don't form a solid. But if we form a solid, then it will be what? Together with the platinum, if it's in the case here, if we put the platinum here. Now, of course, there will be a change in the mass of silver. That is something that is observable if you do that in the lab, which means we can wipe it dry and then weigh it again. We have an initial mass and a mass after the reaction, so we can determine if there was a change in the mass. So in this case, my question is, and I want you to type your answers, right? If we allow this particular battery, voltaic cell here, to proceed, the electron is going that way. So what happens is that your silver is reduced, your silver ions, correct? Silver electrode, okay? Now my question is, what happens to the mass of your cathode? Does it increase in mass or decrease in mass as the reaction progresses? Okay, so type it in. Let's see if we can agree on that. Okay, and then we can go back to, so Rakan says it will increase, obviously, because the silver ion gets deposited as a silver. Remember, look at the reaction at the reduction part. Silver plus change into the silver. So it will attach itself. Silver atoms will now be attaching on the surface, okay? So a lot of you are saying it deposits, it increases, okay? Now, can we address the issue on, what's that? The salt bridge. Okay, now, listen. Remember, let me just push this so that you can see. From the reduction potential, we already determined which one is pushing the electron and which one is pulling the electron, right? In this case, hydrogen is the one that gives up the electron easily because silver would rather be reduced based on its reduction potential. In other words, the silver ion would rather take the electron. So when that happens, this is the electron source, okay? The electron is moving that way. So the moment that electrons are being produced here, because hydrogen is now being oxidized to H+, remember this is our oxidation half, there will be a buildup of charge here in terms of electric potential. Just like any change, the driving force is from a higher to a lower part. So this one, we are creating a large electric potential to a lower potential, so the transfer is going that way, correct? So while this is happening, the electrons are moving, we are producing more hydronium ion in the process. I hope you're following this, okay? As the hydrogen gets oxidized, electrons are pushed outside, and then you produce more of the H+. So as it keeps on going, there will be a build-up of positive charge here, right? Now, it's not being discussed in general chemistry. Even Tyler Dewey did not discuss it because it might not be, appropriate at the beginning. But since you're asking about the role of the salt bridge, since there is an increase in an H+ here, okay, what happens on the other side is that as silver ions are being reduced, so there is a reduction in the positive charge here, right? So what happens is that the chloride ions will migrate where? Where should it go? The cat ions go into the cathode. Why? Because we are depleting the silver ions. So your sodium ions will be moving towards the right part of the cell. so that whatever is lost in terms of the positive charge will be replenished by the sodium ions, which are not reacting. Their presence there is maintaining electrical neutrality. Remember, the short answer to what the salt bridge does, is to maintain electrical neutrality. Electrical neutrality is to make the circuit complete, continuously moving charges. The chloride, on the other hand, will, neutralize the increase in the positive charge here. Now, why is this happening? Now, conduction, gentlemen, happen in two ways: electrical and electrolytic. Okay, electrical is the usual one that we know. The movement of electrons in wires, in our outlets, that's electrical conduction. What we see here in the internal circuit is electrolytic. Okay, what are the moving charges? It's not electrons that are moving in these solutions, but the ions. Okay, so the ions are the ones migrating. Here, it's the electrons that are moving. So both electrical and electrolytic are found on the voltaic cell. So when you say, what's a battery? What's a voltaic cell? What's a galvanic cell? It is consisting of an electrical circuit and an internal circuit. External is your regular electrical conductance. Internal is when it's the ions that are moving. That's why there is continuous movement of charges. If you recall, some of you are in my classes before, I keep on saying that conduction requires two things. Number one, there should be charged particles. Number two, there should be movement, correct? So here, movement of electrons, conduction. Here, movement of ions, conduction. The moment that the ions are not moving, the circuit will stop. That's why it's the job of the ions in the salt bridge to neutralize this so that there will not be a buildup, because the moment the buildup is happening, the reaction stops. Okay, so we can keep hydrogen on pushing the electron. Chloride will keep on migrating on that way. Okay, I hope that helps. Anything else? Can NaCl work as salt for every battery? Well, technically, yes. Why? Because sodium is always sodium. We don't see it getting reduced in our laboratory setup, right? If you look at your reduction potential table, what you see in the bottom are their highly reactive methods here. So they would rather be converted into ions. So Na plus will stay Na plus. Most of the redox processes that we have does not really use sodium ions or potassium ions for that matter, right? Can you use any kind of salt, sir? So normally any saturated salt that is not very much reactive in terms of redox reaction. So we have sodium is a clear cut here, and sulfate salts. So normally, and even chloride salts and nitrates as well. Okay, so here, what is the source of our H+? Remember, in our discussion, we normally remove the counter ion. So the counter ion H+ here is probably chloride, you see? So your source of H+ here is hydrochloric acid. So practically you have chloride here. What's the source of our silver ions? It could be ions, will be a nitrate or a sulfate. Okay, so when you are thinking about writing it down, if I'm going to introduce a cut ion, it could be a nitrate. If I am introducing here, say H+, HCl is a good one because it's a strong acid. It will easily give up the H+. Okay. So Ryan says that's why we can use a battery to return the ions into their original state, therefore making the reaction spontaneous again. Is that true? Now, guys, when we talk about battery as an application of voltaic cell, thank you, Ryan, for that question. There are primary cells and there are secondary cells. So the secondary cells are the batteries that our calculators, our cell phones are using, our laptops, even our cars make use of secondary cells. Secondary cells are rechargeable, meaning we can reverse the reaction. Now, to tell you simply, not all reactions are completely reversible within the conditions that we have. Remember the value of the delta G that we say practically can do reversible reactions? Do you remember the value? What's that? What value of delta G that we can practically work on. So that's negative 100, positive 100, right? So that will give us a good reversibility of reactions. Because if delta G negative is too large or delta G is too positive, it's always on the other extreme. Okay, so good reversible batteries are working on those windows. Okay. Okay, guys, it's 10:20. If you look at the strength of, I want you to read activity number 1 on reduction potential table on Schoology so that you can see the relative strengths. You have seen the previous problem between zinc and copper, so you can totally work on that. So when the salt bridge starts to work, does that mean that the reaction has stopped being spontaneous? No. When the salt bridge starts to work, the salt bridge starts working while the reaction is progressing. It doesn't just, stay there, because once that there is a potential difference, then the ions and the electrons start migrating. They start their movement. So we get electricity if they are moving. Okay? Of course, if the battery stops, either you have reached equilibrium, right? Remember that when a reaction reaches equilibrium, we cannot derive work from there. So what do you do if it's a reversible battery? You charge it into a plug. This time we reverse the reaction. We are now supplying the electrons, making the reaction in reverse, right? So while you're working on it, work on activity number 1. And then we also have an activity 2 for the writing of this one. So now, can I erase this so we can work with another example? Right? Are you ready for that? Maybe we can reverse the process, meaning I'll give you the cell notation, okay? And then we will work out the reverse, meaning we should be able to deduce the reaction, write, or draw the cell from the cell notation, okay? So while you're at it, work on the activity, and then I'll get ready with this one here. Probably I'll just flip this. We can go back to it later. Might need. So let's try this one here for those of you who are ready. We can start the activity. Okay, let me check. Are you talking about the first one? How come? Okay. Let me fix the timing. Maybe it's closed. Activity 1. Give me a minute. Okay, the settings. Okay, can you refresh your Schoology and give me feedback if you can work on it now? Yeah, it says March 11. Big problem. I think I fixed it. Now it works. Okay. I'll give you time. And then I'll work on some here. When you're ready, we can reverse the process. Okay. Okay, thank you. Keep on working on those. Okay, good. Let's wait for the others. Let's wait a bit. Let me refresh that. Okay, only 2 people have submitted so far. Okay, Said is done. Why Kevin? Is Kevin your English name? Let's move this a bit. I need to charge my laptop. Okay, it's fine. Working. Okay, Mohammed is done. Easy peasy. So I'll be checking on your work later. You can always look at the grade book for those graded items. It's a nickname that I used to have ages ago. I got two answers wrong. Why? I'll put comments on those. Yeah, I'm going back to them, remember? So I will be overriding your score on the system if I think what you've written there is correct. Okay, don't worry. Why? Someone got kicked out? Well, when do you compare E-naught values for reduction? Before you flip, remember? So which one has the higher E-naught value will be the one that goes into reduction because a basis of our table was reduction. Okay? Mushkila. What's the mushkila? Okay, so that's a good observation, Muhammad. Okay, you mix up the D ion and the neutral D. Remember, you should identify the oxidized form and the reduced form, right? Because everything else written in your reduction potential table are from the oxidized form to the reduced form. Look at the one on top. Wait, there's a difference? Yes, because D plus is not the same as D. That's two different chemical species. If you say F2 gas, right, being reduced to F minus. So this is your oxidized form. That's your reduced form. See? And it's written in there with a positive 2.87 volts. Correct? So that means the tendency of fluoride to be formed from fluorine gas is very high. Its E-naught is positive 2.87. So if we are to partner with something like chlorine, okay, look at the reduction of chlorine gas. 2 electrons. What's the reduction potential of chlorine? You can see that it's positive 1.36 volts. So which would win? This taking the electron or chlorine gas? I'm not talking about chloride. I'm not talking about fluoride. I'm talking about fluorine and chlorine gases. Which of these will take the electron? Naturally, the one with a higher reduction potential. Therefore, this will become our reduction half. So this will win in terms of reduction. This have to be flipped because this one is stronger. So here you will say 2 chloride. This time you will be using it as an oxidation. And then you flip the sign here. You say negative 1.36 volts, right? So that is our reduction half reaction. See? So here, we'll not be using now this one here because we have, this is not reduction half, this is oxidation half. Okay? What a way to butcher the spelling of my name, fellow weirdo. Why is that? Shamri. It's fine. It's just what? It's just an activity, right? Remember, what is more important is when in the actual test, you should be able to deduce it on your own. That's why we're doing this small activity so that we can, tweak the small items that we normally get wrong. Okay? So again, we flip this. And then what's the cell potential here? We add them up. That's a positive and negative. 7 minus 6, that's 1. 8 minus 3, it's 5. You have a positive E cell here, which is spontaneous. Since both of these are gases, you need platinum to make this work. Okay? Kevin, stop. if that's your name. Okay, you say, obviously, when we calculate for E cell, we sum up the E naughts for after we flip the reaction. Of course, because we are just adding the reactions, right? Reduction half, oxidation half, we add them up. We add up also their potentials. We end up with our E cell. Okay? Okay. I think you're ready. Shall we do this example here? Can you see it? What I want us to do is to reverse the process. Okay? Meaning, if we're given the cell notation, we will be able to deduce the reaction. It says here, determine the half cell reactions and the value of E naught for this cell. Of course, you will need the reduction potential table. I hope you have access to that, but I can help you because I have one here. But remember, it's better that you see it for yourself so that you can decide what to do. Look at this one here. Remember, platinum is our anode here. This is our oxidation half. And this is the reduction part. You see their salt bridge there. And then your cathode is another platinum metal because the reacting species are not solids. Okay, obviously, the oxidation reaction will involve this, right? So if you look at the reduction potential table, there's the reaction of dichromate here with an E naught of positive 1.33 volts in terms of reduction. Okay, are we using it for reduction or are we using it for oxidation? Chromium here is +3 in Cr3+, but remember that chromium in dichromate is a +6, right? So the reaction is practically reversed. So if you look into your reduction potential, let me just copy that here so that you will have a reference. Your dichromate plus 14 H pluses plus 6 electrons will give you 2 chromic ions and 7 water. This has an E naught reduction. Remember, this is reduction, electron gain, 1.33 volts. This is listed in your table. Okay? Now let's look at this one here. Your bromine, okay, which has a value of what? From bromine liquid, okay, plus 2 electrons, give you 2 bromide ions, aqueous, with a reduction of 1.07. Okay? That's the reduction half values. Okay, bromine liquid to bromide. So in this cell, we are saying that we want this, the oxidation reaction, and we want this, the reduction reaction. Okay? So if we do this as our oxidation half, I'll be flipping this, right? Because this is our oxidation reaction here. The oxidation goes from +3 to +6. So let me copy that. 2Cr3 plus 7H2O. Of course, this is aqueous. That's a liquid. What are the products? I have here the dichromate ion immersed in solution plus 14 H pluses and 6 electrons. Since I flip the reaction, then that E naught becomes negative 1.33 volts. And I will be putting now here oxidation because it's not the reduction that's happening now. So the oxidation potential of this one is negative 1.33 volts. Okay? Now in the reduction half reaction, okay, this is the one that we need to have. So reduction. Is this the correct reaction that we have? How does it look like? It says Br2 plus 2 electrons. Bromide ions. Is this a reduction? Comments. Are you sleeping, gentlemen? Is this reduction? No, it's not. What's the reduction? From bromide. Let me write that again. Br2 liquid plus 2 electrons Br minus, aqueous. What's the oxidation here? Oxidation number? 0. What's the oxidation number? Negative. So that's reduction. We are copying that. The reduction potential is positive 1.07. Now the question is, did we get a positive E naught? Okay, can you comment? Yeah, no sleep for the wicked. 0 and negative. What do you mean 0 and negative? So what's the value here? So it will be ending up with a negative value, okay? Negative 1.33 plus 1.07. So that's negative 0.26 volts. Okay? Question, is this a galvanic cell? Comments? You say no? Okay, a lot of you said negative 0.26. So that means this reaction, as written in the cell notation, is not a spontaneous process because it gives you an E naught. But if we reverse it, we'll end up with a galvanic cell, okay? Because if we flip the entire reaction, then we'll end up with a positive 0.26 volts. So we can construct a galvanic cell in the reverse process, okay? So a lot of you agreed, no, it will not create a voltaic cell or galvanic cell because it's not spontaneous because its E naught is negative. Okay, so that's it for now. So we will continue our discussion a little bit later. If you want to work on your activity number 2 in constructing a voltaic cell, you can do so. Okay, so while you're working, you want to work on it now or later, that's fine with me. So you can take a break. I'll just leave this on. Okay, so we will resume at around 11:10 as always. Okay, so Fawaz can scratch his leg. Okay, don't be shy. Go on, scratch your leg. Let me just work on the activity. Let's see. Bader is waiting. So everybody has submitted. That's fine. It's okay if you made mistakes in the activity as long as you realize and which ones you can do later. That's fine. So for those of you who have nothing to do, Mr. Did you know it was Fawaz? Oh, really? Oh, happy birthday to Fawaz if it's your birthday. Unfortunately, you cannot go out. What was Said's question? I didn't understand the difference between the reaction you just erased and the one you wrote. Which one is that? About the fluorine and the chlorine? March 7 was your birthday. Is it this one? Fluoride has positive 2.87. And chlorine positive 1.36. It was a reduction, see? If you're referring to this one. What's the oxidation state of liquid bromine? That's its elemental form. So it has a 0 oxidation number. Bromide monatomic cations, anions take their charge. So it has a -1 oxidation number. So from 0 to -1, that's reduction, obviously, right? So here, it's oxidation from +3 to +6. Okay? So the cell is easily computed, but if you complete this, what's the overall reaction? That's 6 here, that's 2 here. We multiply this, only the reaction, by 3. Okay? The activity number 2 is due at the end of the second period, right? So I'll stop discussing towards the last 15 minutes of second period. If you want to catch up on that, that's an easy one because you just have to repeat what we're doing. But we have to move on with the topics, right? So if the virtual days are extended next week, then we keep on doing live streaming so that I can discuss things with you. Do all reduction reactions have positive E value? No, look at the table here. There are a lot of those with a negative value, see? So those with negative reduction potentials would most likely do oxidation instead. Most likely, they are the ones that gets oxidized. Remember in the discussion, anything below that is the one that gets flipped when you want to construct a good cell. Okay? Yeah, take your 10-minute break. Isn't that what you've been doing so far, Mohammed? Bring me something from the snack bar. There's nothing there. But there is asking, can we get more time to do the activity? It's an easy one. The last 15 minutes is fine. Going to the kitchen. What are you going to eat, Ryan? Go ahead, take your 10-minute break. I'll just be here. So it's 10:58 in our clock here, so we'll start at 11:10. Because you have to watch a video. No, you don't have to. If our discussion here, the video that I was referring to is just a backup, Badr. It's a backup if we didn't get to do the live streaming. Okay, since we have already discussed the salient points in there, you can automatically jump into the activity. It's basically what we're doing here. It's a repetition. Yeah. You don't have to watch the video because we've done the preliminaries, right? Okay. So it's just an application. It's the same. You construct a cell. I give you 2 half reactions, right? You determine the oxidation, reduction, draw the cell, take a picture, upload, and that's it. Don't worry. It will be so easy. I'm starving. Good for you. You are in your kitchen. Uh-huh. I will sanitize you for what? Shh, 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 shh. Yeah, Tom Hanks and his wife got coronavirus. They're in Australia. By the way, they have increased the number of countries with a travel ban here. Philippines is now included. The problem is if after CPP, can we go home? Because we normally go home during July. YouTube streams. Well, we do that during weekends. I just called my mom earlier. Yes, right. I can exit, but the problem is getting back. Because originally you get quarantined for 14 days, but with the rate of spread at this point, it's not good. It's very fast. Now, the number of cases very similar in Saudi Arabia and the Philippines, around 40 plus at this point. Very the same. I'm not sure if you can see that. What's in the picture? Can you tell? That's a 3 feet snake that my dad killed. Look at that. Scary. Oh my god, right. What the cleavage. Not the cleavage, it's a snake. See? The head is smashed right there. Yeah, it's a snake. Look how fat that is. That is a 3 feet long snake.